hardware only, or software only, or a combination of hardware and software. Here, because of the importance of software we feel in the current state of our complex systems, we thought we would do justice in talking strictly about software FAMICAs and software hazard analysis. And, what is unique about software that we should talk about here, and that we didn't talk about when we're just discussing the system. So we provide a discussion on the requirements to, when you find a hazard through software, what do? You want to fix it. We're saying that the best way to fix it is in the requirements. Write a requirement that they can write the code for, and now that fixes the problem. As opposed to, with hardware, a lot of people will just swap out a component, right? The component failed, put the same component back in there, and just keep running. Maybe you got a better part, right? A higher quality part, but it's the same part, same function. Here we're saying, no, you got to go in and touch the code. You got to change the design. In the case of FAA, the FAA, back when I was there, it cost $1 million. It's probably much more now. But it was $1 million to change one line of code on a flight, on an airplane, let's say a flight management system or a flight control computer. $1 million back in the day, probably much more now. So you can imagine that if there's a lot of money to certify software changes, you got to do a good job of writing those requirements. You don't have to spend that money to fix the problem in software. So these are the last two chapters. Lessons learned is chapter 17. This was something that was really tough because it had lots of lessons learned. Like I said, I could talk a day on any one of these subjects. This is one that maybe it would take 2 or 3 days to talk to. All the things that we discussed and the things that we didn't discuss. Like we were saying, hey, I had this lesson learned. We just started brainstorming, right? Just thinking with my partner. We're saying, hey, these are all the things that happened to me, and I started writing notes and saying, I really want to talk about this. And then when I was explaining it to him, he said, nah, I think that's too close to this other thing. We're already going to accept this lesson learned. This one's too similar, so we don't want to have 2 very similar lessons learned. So kind of, strip some things out. And, by the time we got to the point where we got to write this chapter, and it's not going to be 50 pages. It's going to be, 20 or 30 pages. I felt like I threw out a lot of gold nuggets that I wanted to keep. So it was kind of a strenuous activity to throw some things that I thought were good ideas to talk about when we're trying to limit the page count. I think the number of pages in the book is 500 pages. And when we originally signed the contract, it was for 300 pages. So if anybody has seen my first book, that was about what we had promised 300 pages, and we delivered 300 pages. So it's about, maybe about half the size, maybe a little smaller than half the size of this. But we said the same thing, we'd do 300, and we actually delivered over 500 pages. Because there's a lot that we want to talk about, and then there's a lot that we threw out. So it probably would have been 1,000 pages of most of the stuff we did write about stayed in here. So we also talked about special topics. Oh, before I go on to that, so we discussed the process of capturing lessons learned. So not only did we disclose lessons learned that impacted our lives, but we said, how do you capture lessons learned? How do you store that data? How do you use that data? How do you provide continuous improvement? How do you show people that, have these cases, these like case studies that I could show in a trade study that says, if I'm doing a cost-benefit analysis, here's something that happened. This is a case that happened in this situation. We don't want this to happen again, so we study that case, and then we provide, if you spend the money to prevent what happened here, it's going to give you this return on investment. And that's how you get to a cost-benefit analysis, evaluated benefit of doing a design change. So we talk about that, and the process for continuous improvement, constantly collecting the data, collecting the lessons learned, analyzing that data, and then making recommendations to improve things. And then the last chapter is on special topics. Here is where we did the deep dive into the industries that we were really familiar with in the commercial transportation with airplane and automobile. So we examined a lot of the historical data over the years to show like safety metrics at a high level, things that were on the public domain, the internet had these. We also pulled in a lot of data that we knew was copyrighted, but we wanted to study it. So we had our own reading material, and then we wanted to publish it, and then we had a problem getting approval. Like I remember I pulled some reports that I had from one of the airplane manufacturers, I won't name names, But this one airplane manufacturer, very popular, reported some data that I had, and I thought, can I share this in the book? And so we wrote to them, the publisher said, you gotta get a release for all this if you're gonna cite their work. So we wrote to them and said, hey, could we use this material? Oh, no, that's proprietary. It's not just copyright, it's proprietary. I said, okay, I didn't realize that. And so, how'd you get that material? Kind of quizzing me on, well, come on, it's 10 years old. It says, oh, okay. First it was like, didn't matter, or first it did matter, and then it didn't matter. Oh, it's only 10 years old, okay, well, we won't sue you, but don't release it, right? So they wouldn't let us release it, so we had to take that stuff out of the book. And in some cases, we didn't replace it. In other cases, we did. We took some material out and found a place in the public domain that we cited, and we referenced it. So we used, our public domain data sources to show you historical data, historical trends, analyzing that data. We also looked at some recent data to compare what was happening in history compared to what's happening now. Looked at both those industries and tried to draw a correlation. Like when I talked about the wind shear computer, this is something that has to happen because an airplane is existing in a 3D space. A car doesn't have to deal with 3D space, right? It's on two dimensions. But one thing we did find is TCAS. So if anybody's familiar with TCAS, which is Traffic Collision Avoidance System, we cited that as another safety system that was designed in the commercial air transport industry to prevent hazards from two planes colliding with each other. So that's why this system exists, right? TCAS is two planes coming at it and they coordinate which way they're going to turn, right? So let's say they know they're coming at each other and they both turn the same way, right? I'm going to take a right turn, hard right, and I'm going to take a hard left, and now you're turning right into each other, right? So this is to coordinate that, say, okay, you turn right and I'm going to turn right, and now bypass each other. So that's just a way for the systems to coordinate. We thought, hey, with Google cars and all these autonomic vehicles, autonomic transport devices that are existing today, whether it's robotics controlling it or they're being controlled from a network, all these things that are now out without a human in the loop driving the vehicle, wouldn't it be nice if they had some kind of a TCAS? Well, actually they do. They have a form of a TCAS with the different kinds of sensors and the predictive analytics on board. They're using machine learning algorithms and predicting whether something is going to be an accident, but they still miss some things, right? So that even though they're using machine learning, the machines still have to get smarter. So they still have to detect other things that they haven't found. Like, Phoenix is a perfect example, right? Phoenix is like a test bed for a lot of these autonomous vehicles on the highways out there. And one of the accidents that happened, which was in the news, was they hit a person, right? Because it was not big enough to see this person jut out in the middle of the road and the car hit him. And I think there was another case where it was a bicycler that got hit. So it detects big systems, and it can detect an automobile that's fairly large, but it doesn't detect smaller objects and ones that are moving faster, let's say, than a car that moves out in front of an oncoming vehicle. So we explored that, and we explored the benefits of commercial air travel that could be leveraged with the automotive manufacturers and the developers of new ground transport systems. So that's the idea of taking a TCAS from the from the aerospace and putting it to automotive applications. And then lastly, we talked about the future improvements in commercial space travel, which is really interesting because NASA has a lot of that responsibility, and now that's going to be commercialized, and so that's going to the FAA. So that's interesting to see this crossover from what was strictly NASA responsibility to now commercial FAA responsibility. So, final thought. So this is something I extracted from the introduction or the preface in the book, which is how do we address these different questions that any good engineer should address. So this is not strictly something that a safety engineer needs to address. It's any developer or designer should address these questions. And so one of my motivations in writing this book was to think about what a modern day hero is. How do we look at an engineer? Is an engineer actually a hero? I mean, I've seen engineers that do great jobs, right? That are stellar in how they think about the future of certain products being used. And so an engineer you know, whether they're a good or bad engineer, should ask these questions, and then depending on how they ask those questions, I say determines whether they are heroes or not. And, you know, a lot of the engineering roles that we have, there's people that are doing heroic work, but they don't get recognized. And I see it all the time in my career, 35 years in the industry with, you know, 9 different career changes. So I've noticed this one common thread is that engineers typically don't get recognized unless they're bringing in money, right? If they're bringing in business to the company, they will get recognized. But what if they're preventing failures? They're preventing liabilities, they're preventing losses, right? They don't get recognized as much. Even though, you know, design for Six Sigma does some of that, you know, any Six Sigma process, lean manufacturing, you know, that's kind of the role of an engineer to save money in manufacturing. But again, it's to streamline the process and make it go faster, which could make it more prone to risks of failure and hazards. So you really have to be an unsung hero. And so what I did is I said, you know, I'm going to dedicate this book, you know, for those heroes, people that normally don't get the recognition, and try to instill that, you know, reading this book, you will get the tools that will make you that unsung hero. And I referenced this article I read in the IEEE Spectrum back in July 2015. So this is around the time that I started writing this book, and that influenced me to make this claim. Yeah?
I have a question for you back on the amicus and, you know, trying to analyze what your faults would be and prevent them. It seems like when I've seen that done, usually there's a quality department that gets together with some of the system level designers and comes up with this design amica. And yet it often seems to be detached or too high level to really pick up on small defects that can ripple through the system and be catastrophic. And so what have you done in your experience to try and get enough levels of people doing the amica type work to really get it down to be useful? Like, say if you're looking at a circuit, I've been surprised at how many I've seen that were only considering opens and shorts.
Yep.
And yet anybody that's done any kind of failure analysis knows that a lot more can go wrong, and it usually isn't that simple.
Yeah. We call that fracas amica feedback loop. So we'll take all of the fracas events that occur from that type of a design, and we feed that as input into the amica process. So all these things that happened to us in the past, that's like the lessons learned. You know, here's the failure modes that happened to us on these similar type of systems, and we need to consider that when we're doing our amica. So consider this, consider this, consider this. Can this happen to us? Right, I see a lot of programs where they tell me when they look at their fracas that, oh, they solved this problem, they detected it, they solved it, and it won't happen again. And I tell them, you're right, it won't happen again for you, because you're on a program that has experienced this. But what about the next program that reuses your design, and they don't know that you put something into that design that prevents something, and they look at it and say, what's this filter in here for? This isn't needed to detect anything. So they take all this hardware, and now they're repeating the same mistakes that happened from before. I can't tell you how many times I've seen where people look at a schematic that aren't the original developers, and they're trying to reuse something. And they're saying, we're spending all this money. They've been told, I got to cut down the cost of this bill of material. So they start killing all these components and say, this is not value added. And you're right, maybe an EMI filter's in there for a worst case scenario, and it's not necessarily needed. But they take them out, and now you have this sudden condition that, you know, that doesn't happen that often, but it still happens. When it happens, it can cause a catastrophic event.
Yeah, and I think a lot of the designs that are out there, I know from missile designs all the way to pacemakers, the designs have been around for 30, 40 years. And, you know, they might have been miniaturized, and they might have been, you know, gone from, you know, components to more of a IC solution or whatever, but the basic schematic's still kind of similar. But now I see large corporations trying to cut corners, and the first thing they say is, well, let's tear out the input protection circuit. And you're like, you know what I'm saying?
Yeah.
And
I see a lot of times where the input protection circuit is not needed anymore. Like in the case of an LM139 that I designed in back a long time ago. It was a National Instruments LM139 comparator, and we were buying a mill standard part, and it had a note in the app notes, in the spec, that said never take the inputs below 0. So we said, well, we're not gonna, I mean, we got a hard rail at 0, so it's on ground at 0, and it goes up to, I can't remember what the input was, like 5 volts or 12 volts. So we had that input rail, you know, set for these two, you know, up and down, high-low decisions, but we were getting these failures. And we duplicated those failures in the lab, we put a socket on there, kept putting these LM139s in there, and kept getting them to fail. And we realized that it was happening because of ground bounce. So we were flipping a switch, and because of the DVDT response, right, it was going below 0. And that was failing. It didn't take much just to cause it to go fail. So then I bought a bunch of new 139s. They weren't mill, they were commercial from National, and they didn't fail. So I tried to figure out why would the mill parts fail, which is 10 times more than the commercial part, you know, cost. And the commercial part lasted. I put 50 parts on the socket, did the tests, never failed. So I called up the manufacturer and I said, what's the difference? He goes, oh, these got these snubber diodes on the inputs. So there's no way you can get a back bias. So now, if you had any protections to prevent that from happening in the circuit card, you know, like say series limiting resistors, you can take that out because it's now embedded in the device. I can give you all kinds of examples on power circuits where that happened, where you had one device and now that device changed design for the better or for the worse, and now your system is either performing better or performing worse, and you're wondering what happened. Well, the part manufacturer changed something in the design. So I think for the general Famica, the answer I was thinking of in the beginning when I was going to go back to one of my slides is there's different levels of Famicas, right? So I could do a very detailed hardware analysis, and I've done this in the past, where I was an engineer on a program, and I spent over 2 months working on a circuit card, so one single circuit card with about 20 components, doing a Famica, and that's all I did, right? That luxury doesn't exist for me anymore, but that kind of rigor is what it takes to do some of these detailed analyses on a circuit card level. At a system level, you don't have to do that kind of rigor. You're looking more at a top-level system, subsystem functionality, and now you're looking at what are the systems doing that can be tolerant to faults or recover easily from faults, or have a single point failure where you've got to take out a whole system, and now the maintenance and the repair costs are astronomical. I got so many examples of that, but I don't want to disclose any of that at a top system level because it might be embarrassing if this tape goes far. But it could be very catastrophic and very costly at a system level if you don't do the detailed functional analysis. Not getting into single piece parts, but just looking at how does the system function when a failure occurs. You know, does it have fault tolerance architecture to it? Does it have error checking, error correction coding? Yes?
Did you cover, for lack of a better term, I'll use the term forensics, like black boxes, various things? What part would that have come under in the 18 sections that you, or is it its own?
I would say it's under it's several places. Let me go back to the paradigms. So it's going to fit in the paradigms section. So in the chapter here, at the end of this chapter, we have a table. It says, for these paradigms, here's what we touch on those. So, you know, zero defects would be one of them. Preventing accidents is another. You know, looking at single causes versus multiple causes. So all of those causes are root cause analysis that comes from practice. So the forensics, the triage, all that analysis gets captured and stored and then reused again when we do the next Famica. And I know the chapter under testing covers it too. You know, we talk about data collection and test results. Maybe this one a little bit. Wrong practices, part of like a process Famica, doing triage of what's causes of manufacturing defects, workmanship defects. Yeah, it's right, and there's no chapter on fracas or triage or forensics, but there is touched on throughout the book. Any questions?
Yeah, about reliability.
Yeah, the reliability book covers it in
Oh.
detail.
Yeah,
So it's got two
that's the
books.
right answer, Lou. This guy's a salesman.
Thank you, Bob. Okay, thank you.
Thank you, Lou.